Manufacturing and process operations face a host of ongoing operating challenges that impact their growth. These challenges include maximizing safety, cost savings, productivity, and process uptime, while addressing environmental concerns and regulatory compliance. Fortunately, CECO-Environmental enables industrials to grow with clean, safe, and more efficient solutions that protect our shared environment. We offer products, services, and solutions to efficiently improve your air quality. If you know what you need, you can custom order it from us. If you don't, then we can diagnose your situation to meet your specific requirements. At CECO, we can help you at any stage in the asset lifecycle, whether you need an assessment to help you plan for growth, or even to help uncover solutions that drive more uptime and reliability while driving greater efficiency. CECO can deliver a solution for you. Our lifecycle solutions range from the appropriate parts required for operation through preventive maintenance, through multi-year service agreements that allow you to focus on your core competencies while we help drive improved asset reliability. Our technologies include regenerative thermal oxidizers to abate volatile organic compounds, fume exhaust solutions and fugitive fume filtration, mist eliminators for liquid mist and aerosol emissions, industrial cyclones to remove particulates from an air, gas, or liquid stream through vortex separation, baghouse dust collectors to collect dust and other impurities from air or gas, wet and dry scrubbers to address hazardous gases and odors, versatile modular and clamp-together duct components, and custom duct to integrate our technologies into a complete industrial ventilation solution. For more information, please visit our website. Click on the How We Can Help You tab, and then select Challenges for Air Pollution Control and Product Recovery. CECO-Environmental, your partner for improved air quality.
Welcome, and thank you for joining us today for our first CECO Certified Continuing Education Series webinar. Today, we will be learning about Cyclone Fundamentals presented by CECO-Environmental. My name is Mary Rusnak, and I'm the Marketing Manager for the Industrial Solutions segment of CECO. With me today are my teammates, Mike Clark, Business Development Manager, and Mark Salamone, Sales Manager for our South region. While we wait for everyone to join, I'd like to go over some basic information about our webinar platform and also the PDH certification. First of all, if you're having sound issues, one of the first things to do is take a look at the media player, which is the green arrow, and check and see if you're muted. You can also take a look at the help widget, which is the question mark and the blue arrow, and see if that can guide you through. Finally, log in and log out using the link from the email when you registered, and that might also be able to help. At the bottom of your screen are multiple application engagement tools you can use. All the engagement tools are resizable and movable, so feel free to move them around and to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool. Keep ourselves on track today. We've got a pretty long presentation. We're going to hold all of the questions until the end, but you can submit your question at any point in time. If for some reason we don't get to your question live, we will contact you later, so don't worry, you'll get an answer. A copy of today's slide deck and additional help materials are available in the resource list over on the left-hand side. We encourage you to download any resources or links that you might find useful. We have links there to our LinkedIn page, Facebook, YouTube. All of our events and schedule are available on LinkedIn and Facebook, so we encourage you to follow those, and that way you'll always know when there's an upcoming event. The cyclone summary is something that would be a useful reference for taking the PDH quiz later on. Hint, hint. There is also some information there on the professional development hours and basically the states that we are able to provide PDH credits for. We are able to offer credits in 36 states at the moment. And again, just talking about the widgets on the bottom, if you hover over them, you'll be able to see what they do. There's a couple different options there: share via social, email us direct, and then finally the two widgets that are most important if you're here for the PE credits, the test here and the track here, which is on the bottom. Test here is green and track here is on the blue. So when you're ready to take the test, go to the green widget, and if you want to see how far along you are, if you've completed all the requirements, you want to use the blue widget. After you've completed everything, you can go to that tracker widget and you'll be able to print out your certificate. So webinars are very bandwidth intense, so make sure you close out any unnecessary browser tabs, and that'll conserve your bandwidth. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. And if for any reason you get behind, push F5 on your keyboard and that will refresh and push the slide forward. You can also find additional answers to common technical issues in the Help tool. An on-demand version of the webcast will be available after the webcast and can be accessed using the same link that you used when you first logged in. All interactivity remains, including the testing capabilities. So just finally to go over the portion of the PDH overview, today's webinar equals 1 professional development hour. You must be present for at least 50 minutes, and you must complete and pass the test, and that's basically 8 out of 10. When you're done with all of the requirements, make sure that you print out your certificate, which is with that certification widget. We suggest you keep a log. CECO will keep records for 6 years. And if you have any questions, just email me, mrosnack@onececo.com. And I'm going to turn this over to Mark here to talk about the overview of today's topic.
Thanks, Mary, and welcome everyone to the webinar. Today we will cover the fundamentals of cyclones. We will start by explaining what a cyclone is, including the different processes and industries where you can find this equipment, along with the types of engineering codes and standards that can be met per the cyclone design. We will cover particulate matter, including the equipment selection process resulting from wet or dry particulate collection needs. We will then do a deep dive into the cyclone anatomy, including performance needs and guarantees that can be met, as well as pre-testing that can be done to aid in the design of a cyclone system. We will explore the multiple cyclone arrangement options and the advantages and disadvantages of these arrangements. Our technical expert, Mike, will walk you through the different design considerations that need to be taken into account when engineering a cyclone unit, such as inlet velocity, pressure drop, a particle size of the exhaust particulate. Since dust can be explosive, we will explain the measures taken to satisfy NFPA design parameters, which are standards set by the National Fire Protection Association. And finally, we will cover troubleshooting techniques and preventative maintenance measures that can be taken to avoid downtime, including photos of these issues we have personally seen occur in the field.
Okay, and we're at our first poll question for the webinar to gauge a little bit in terms of experience of our audience. And you're going to have the opportunity to input your answer in the next slide. But how much experience do you have with cyclones? A, I'm an expert. B, I have some experience. B, or C, I have a little experience. Or D, what in the world is a cyclone? And you can answer in this slide here. and don't forget to hit the submit button. We'll give everybody another chance here, a couple more seconds to answer, and we'll take a look at the results. Okay, let's look at these results. So let's see. We've got majority are in the a little bit of experience or some experience, and some don't are there with me and D. So right. So this is good. I think that the presentation that we have geared for you today is going to definitely help both people who have a lot of experience with the cyclones as well as those that are looking to gain additional knowledge. Turn this back over here to Mark.
Thanks again, Mary. I can see from the poll questions that we have a nice split between an audience of people who are pretty familiar with cyclones and others that need Cyclone 101. So this is a good audience. So what is a cyclone? A cyclone is a piece of equipment that is used as particle separation device. The equipment uses the principle of inertia paired with centrifugal force to remove particulate matter from the process air streams. There are a few options available for removing particulate matter from the airstream. Cyclones are just one of many air pollution control equipment options. Cyclones can be used as pre-cleaners or to filtrate the larger pieces of particulate from the airstream before sending the exhaust air to a different piece of equipment, such as a scrubber unit, baghouse, or an oxidizer. Multiple cyclones can be used in parallel or in series to increase collection efficiency while maintaining a tight footprint or overhead constraint that may be present on site where the equipment will ultimately be located. These multi-cyclone arrangements can be used in parallel, such as a quad pack or six pack, which we will show design examples of later in the presentation. A cyclone size, configuration, and material type can vary and is dependent on the volume of gas stream being handled, the makeup of the particulate matter within the gas stream, and the removal efficiency of the process that is required. Cyclones are used in many different industries and processes. On the left is a list of typical industries where you can find cyclones, and on the right, there's a list of the processes that occur within these industries that contain cyclones as well as many other types of air pollution control equipment. Within the food and beverage industry, you may find a cyclone being used within a dryer system or a roaster to capture any nuisance dust. An example would be in the cocoa bean drying process used to make chocolate products. During the drying process, particles are released into the dryers that need to be captured. Another example would be shredders used within the metals and mining industry. Cyclones are used to capture larger pieces of scrap metal before sending the airstream to a baghouse, oxidizer, and then scrubber unit, and eventually exhausting the clean air to the atmosphere. Within the chemical industry, cyclones are used to capture powders off the main process lines. These powders can then be used in downstream manufacturing processes of other chemicals. Within the petrochemical industry, cyclones can be found downstream the refining process within fluid bed dryer applications. This is an application where the gas is injected into the bed of catalyst, causing a chemical reaction. A cyclone is used to capture any excess catalyst or fine dust that remains in the gas stream. And finally, within the wood processing and building products industry, cyclones are widely used as particle recovery devices, allowing for the use of recycled material back into the process and cost savings. Cyclones can be designed to meet the codes and standards that we have listed on this slide. Cyclones can be designed to meet the codes set by the American Society of Mechanical Engineers, the American Institute of Steel Construction, the American Society of Civil Engineers, European Pressure Directive, Chinese National Standards, and International Building Code, as well as the AWS standards. The most common AWS standards that we encounter are AWS D1.1, which is typically used in low-pressure carbon steel applications, as well as AWS D1.6, which is used in low-pressure stainless steel construction. Any high-pressure systems with 15 psig or more call for ASME pressure vessel design standards. Cyclones can be custom designed for a particular manufacturing process, environment, and application. You can see on this slide we have listed the different material types we have used in cyclone designs, including special internal and external designs and material types. From our experience, 90% of cyclones are designed and manufactured from carbon or stainless steel. However, other alloys such as Hastelloy can be used as corrosion-resistant materials when dealing with the corrosive particulate. The internal surface of the cyclone can be designed using different material types. An example would be a polished stainless steel interior that is used on a sanitary process within the food or pharmaceutical industry. The exterior of a cyclone can also be custom designed for the process and environment of the equipment. For example, we've added heat tracing or steam jackets on the exterior of cyclones to stop condensation from forming inside the vessel. We've also added to a process where the need for exterior cooling was a necessity to stop particulate matter from sticking to the internal sides of the vessel. You've probably heard me mention particulate matter a few times. So what is particulate? Particulate is small, minute-sized, separate particles. A typical particle is measured in microns or micrometers. 1 micron is 1 times 10 to the negative 6 meters, or 1 millionth of a meter. Dust particles are measured from 1 to 100 microns in diameter. These are small particles. To give a better understanding of how small these particles are, we will show a table on the next slide which compares the particle to a human hair. Particles that are less than 1 micron in diameter are considered fume or smoke. When we talk about human and animal health and safety, we are mostly concerned with particles 10 micron or less in diameter, as these particles can easily be inhaled and trapped in the respiratory system, resulting in health complications. So as I mentioned, if you look at the graphic on the right, you can see the human hair is around 50 to 70 microns in diameter. You can also see the comparison of human hair to a grain of fine beach sand at 90 microns in diameter. This should help give a better idea of how fine the particulate being captured in cyclones actually is. On the left, you can see another chart comparing the human hair to a light, average, and heavy dust particles, which is between 1 and 10 microns in diameter. And again, if you look to the bottom, you can see that tobacco and cooking smoke contains particles less than 1 micron in diameter. This slide should help to show the different types of dust and particulate that are within the particle filtration range. Again, if you look at the top of the page, you can see the human hair at 75 microns in diameter. This hair falls on the bottom right side of the particle filtration area of the chart. You can also see fly ash, coal dust, cement dust, and a few other fine dusts used as comparison. As you move to the left on the chart, you move into the fume and smoke size particle ranges. As discussed, some particles contain moisture and some particulate is dry. The table shown on the prior slide shows particles that were wet mist within the 10 to 100 micron range. So how do we decide if our equipment will be designed for wet or dry collection? Major processes and site conditions to consider are whether or not the particle is sticky or in a humid gas stream. Is the dust combustible or explosive? Is the process a mix of semi-liquid particles that can be reprocessed? And is the water easily accessible? If all of the above are true, then wet collection systems would be the most efficient design for this application. However, if water is not available, the collection dust needs to remain dry, and contaminant has a low moisture content, along with floor space being plentiful, then a dry collection design would be the most efficient design to pursue for this particular application. This slide shows the different types of wet and dry particulate collection devices that can be utilized. The picture on the right is a scrubber unit. Scrubbers are used for wet particulate collection. In the middle, we have a baghouse unit. A baghouse is typically used when a cyclone is impractical because the particles being collected are extremely fine and the outlet loading or emissions is highly regulated. On the left is a sneak preview of a quad pack cyclone unit. We will cover all the possible cyclone arrangements and configurations later in the presentation. Also, it's important to note it is not uncommon to see all of these equipment types on manufacturing sites servicing different process gas streams. Now I will turn it over to Mike Clark so he can explain the advantages of a cyclone compared to a baghouse or scrubber equipment shown on the prior slide.
Thank you, Mark, and thanks everyone for joining us today. I'll start with talking about some of the advantages of a cyclone. A cyclone can be the most economical form of particle separation. It's a very simple device in that it is purely a weldment. There are no moving parts. They're very simple to operate and maintain. And because of this, they lend themselves well to severe applications, such as where you have high temperature, high pressure, or corrosion, explosive dust, etc. In the sanitary applications that Mark mentioned, they're also very well suited because there's no product contamination between batches. Cyclones can be equipped with clean-in-place nozzles so that they can be cleaned and sanitized between batches to minimize that contamination. This slide shows the basic anatomy of an industrial cyclone. Dust-laden air enters at the top left through the gas inlet. As the air and dust enter the cyclone and spin around the body, the upper cylindrical portion, and down through the cone, the tapered portion below the body, particles are moving toward the wall to be collected. As they move to the wall and get to the bottom of the cone, they enter a dust receiver, or sometimes called a vortex breaker, and that is a hopper where the dust particles can disengage from the spinning vortex. The particles disengage and fall to the bottom and out of the cyclone. They generally exit through some type of seal device or into a container below that's sealed. The clean gas stream, or the clean gas vortex, returns back up the center of the cyclone, indicated by the blue line, and goes through the outlet pipe or vortex finder. The outlet pipe extends down into the cyclone from the roof, and the gases can either exit vertically, or as shown on this picture, the cyclone can be equipped with a horizontal outlet, often called a scroll outlet, that turns the gas stream horizontal and also breaks the vortex for equipment downstream. There are two main factors that determine cyclone efficiency. One is how quickly the particle moves to the wall to be collected. This is influenced by the centrifugal force and the inertia. The centrifugal force is proportional to the inlet gas speed coming into the cyclone, and we'll talk about that later as one of the design parameters. But it's inversely proportional to the body of the cyclone, the body diameter. As the diameter gets smaller, the centrifugal force is increased. The other factor affecting cyclone efficiency is the length of time that we allow those forces to act on those particles. It's also referred to as the residence time of the cyclone. So you'll see in the presentation that many high efficiency and ultra high efficiency cyclones are much larger in size, and that is to increase the residence time or increase the time allowed for that force to act. This gets very important as the particle size gets smaller. Two main factors can describe cyclone performance. Cyclone suppliers will generally supply a pressure drop across the cyclone at the application conditions. The pressure drop is simply the difference in static pressure between the inlet and the outlet of the cyclone. They'll also describe the cyclone performance in terms of a fractional efficiency curve. Cyclones are more efficient at larger particles and less efficient on smaller particles. Therefore, there's a curve to their performance, and each cyclone for the application will have a certain curve associated with this performance. In order to design and specify a cyclone correctly, we need to have the correct data. And we can divide that into two groups, mechanical data and process design data. For mechanical data, that's dealing with the construction of the cyclone and the mechanical and structural integrity of the unit. This is process temperature, pressure, corrosion allowance, any special materials of construction, exterior coatings or linings on the interior, etc. For process data, which relates more to the performance of the cyclone, at the minimum, gas flow, a volumetric flow, as well as gas density, gas viscosity, and particle-specific gravity. Those four items are required in order to calculate and predict a fractional efficiency curve for the cyclone in that application. Sometimes gas density or gas viscosity may not be available. So given the temperature, pressure, elevation of the installation, and the gas composition, those values can be calculated. Particle loading is also important, especially in high load applications, to ensure the cyclone is designed correctly to handle the material loading, but it also has a factor on collection efficiency as well as pressure drop. And knowing the collection efficiency required allows us to pick the correct cyclone arrangement or the correct cyclone family. And we'll discuss cyclone families in a moment. If we're given the particle loading and the parameters above, the particle size distribution of the particulate we're capturing, that will be necessary to determine the overall collection efficiency by weight. So I mentioned the fractional efficiency curve, but if we have a distribution of the material, we can use that distribution to determine that overall collection efficiency. And for a distribution, many of you may be familiar with physical particle size distributions, which can be simply a sieve analysis. Cyclones care about the physical size, but because this is an inertial separator, they also care about the particle characteristics in terms of its surface roughness, its mass, and its shape. Basically, the cyclone wants to know, how does the particle move through the gas stream? How easily does it move through that gas stream and be collected? And this is referred to as an aerodynamic particle size distribution. Sometimes the distribution is available from stack test methods such as an cascade impactor test, but oftentimes we are able to get a sample of the material. And this slide shows a sample from a wood product application. The first thing we would do is to sieve the sample to 150 micron. The bag in the back of the photo is the original sample received, and the pan on the left is the top of a 150 micron mesh or a 100 mesh, and the pan on the right is the fines, or the in this case wood flour that pass through the sieve. We do this to determine the percentage of fines in the sample. Next, once we have the percentage of fines, we take the fines and analyze them through liquid sedimentation. This is just one method of getting an aerodynamic distribution, but liquid sedimentation utilizes a method where we put the sample into a liquid and measure how quickly it settles. The machine then determines a Stokes equivalent diameter for the sample. It takes the irregularly shaped particle and converts it to a solid sphere of the same mass that would have the same terminal velocity. And the reason we use Stokes diameters is because those are very predictable, and because our fractional efficiency curve is developed based on Stokes diameters through empirical testing using that method. I mentioned previously about cyclone families. You may have seen cyclones are designed based on the airflow or gas flow volume in the system. However, a cyclone family is a cyclone that is proportional in dimensions for a range of gas flows. For example, a cyclone that is sized for 10,000 CFM versus 20,000 CFM. It would be two separate size cyclones, but if they're in the same family, their dimensions would be proportional. A different family would have different proportional dimensions for the same gas flow. In the image on the left, the blue cyclone in front is representative of a standard efficiency cyclone like might be present before a baghouse or a scrubber as a pre-cleaner. The cyclone in the back is an ultra-high efficiency cyclone that would be used for environmental emission standards or to recover an expensive product. The difference is the size, and they're both all designed for the same gas flow, but the back cyclone has a much higher residence time, which gives a significantly higher efficiency on fine particulate. Cyclones can be arranged either in parallel, where the gas flow comes in and is split between multiple cyclones evenly, or they can be arranged in series, where the gas flow comes into the first cyclone, and then the exit of that cyclone goes to the inlet of the second stage cyclone. In the first scenario, the pressure drop across the cyclones are that of the individual cyclone, plus any manifold losses. In the second scenario with series cyclones, we must remember that the pressure drops will add, just as they would with any other equipment in series in a system. Some of the advantages of parallel cyclone arrangements, or when you would choose a parallel cyclone, is when you're looking for a higher collection efficiency than you can achieve practically with a single cyclone. Also, a parallel cyclone will have lower energy consumption versus a series cyclone arrangement. Parallel cyclones are often used when there's a headroom constraint or space constraint, such as retrofitting into an existing application where they want improved collection efficiency. Some of the disadvantages of parallel cyclones is obviously they're going to have a higher cost versus a single cyclone. They'll have a larger footprint, and they may have multiple dust outlets, which will require more thought when developing the material handling process. And I'll give it back to Mark to go through some examples of parallel cyclones.
Thanks, Mike. As Mike explained on the prior slide, there are many advantages of parallel cyclone arrangements. We will cover the different arrangements in the next few slides. Here's an example of a dual cyclone in parallel. On the right, you can see the isometric design drawing of a dual cyclone, and on the left is a picture of a dual cyclone in parallel being fabricated. This cyclone was provided to a wood planer mill facility. The large high-efficiency cyclones allowed for a cost savings at the plant by eliminating the need for a baghouse downstream the cyclones. Headroom at the plant was not limited, which allowed for this design. You can see the large air header in the picture with the 4 explosion panels. This is an example of a triple cyclone arrangement in parallel. In this view, you can see that the process duct comes to the units from the east side. The inlet duct reduces in diameter to each unit, allowing for a balanced system. This allows the 3 cyclone units to fit in a particular location while still utilizing the high efficiency design and parallel arrangement advantages. Here's an example of a quad cyclone parallel arrangement. The left picture is the actual work in process of the outlet manifold of the isometric design shown on the right. This cyclone arrangement was used in a baby formula manufacturing process. This is a sanitary process which specified a polished interior. This arrangement also included a clean-in-place piping system, which allowed for cleaning to take place in between manufacturing batches. This is a picture of an ultra-high efficiency 6-pack cyclone. If you look closely at the picture, there's actually 2 6-packs in parallel for a total of 12 cyclones. These particular units are used in a mining application. The gas stream is coming from the mineral roaster and sent through the cyclones for efficient product recovery. And lastly, here's a picture of an 8-pack cyclone located at a facility that manufactures plywood for the building products industry. The cyclone is downstream of a wood dryer. These particular units are acting as pre-filters by removing the fines from the gas stream before conveying the exhaust to a wet electrostatic precipitator unit.
Thank you, Mark. And we're up to our next poll question here. Same as the previous one that we had, you'll be able to put your answers in the next slide. So what are some advantages of parallel cyclone arrangements? Answer A, high collection efficiency. B, lower energy consumption. C, multiple dust outlets for material handling. D, which would be A and B, or E, all of the above. So think about that one. There might be a little bit of a tricky question in there, okay? And you can put your answers here. We'll give everybody a few seconds here to think about it and get their answers in. Okay, we're gonna, couple seconds, and let's take a look and see what the results are. All right, most of you picked up on that tricky part of the question here. It is D, which is high collection efficiency and lower energy consumption. The tricky portion of that was C, which actually is a disadvantage. So good job to everyone who got that one. And I'm going to pass this on now back to Mike.
Thanks, Mary. We've discussed parallel cyclone arrangements. Now let's talk briefly about series cyclone arrangements. Some of the advantages to a series cyclone is that you do get an increased efficiency versus a single cyclone. Often series cyclones are used to add redundancy to the system. If you have a system that is very critical and concerned about plugging or failure of the first stage cyclone, the second stage cyclone could be there as a backup in case you had a fault with the first cyclone. And often in systems where we see series cyclones, the first cyclone may be used to collect very coarse or heavier material to return that material to another part of the facility, and then the second stage used to collect the finer material and take that to a different place. So it's somewhat of a crude classifier. The other reason for that is the first stage cyclone will take the bulk of the loading. So it can be constructed to withstand a higher abrasion rate. And then the second stage cyclone is more of a polishing cyclone and would not need quite as strict requirements from abrasion design, or could be operated at a higher velocity. And we'll talk about velocity versus abrasion in a later slide. Some of the disadvantages of a series cyclone is obviously there's an increased cost versus a single cyclone because you have 2 cyclones now versus 1. And there's also an increased energy usage versus a single or parallel arrangement. As I mentioned previously, the 2 cyclones in series would add when considering their pressure drops. These images depict a series cyclone arrangement. The image on the left is an ASME pressure vessel cyclone with a refractory lining. And you can see out of the roof of the cyclone where the clean gases are coming out of the first stage, we've used an elbow to elbow into the second stage cyclone. So the gases leaving the first stage go into the inlet of the second stage, and then are separated and leave the second stage. Now the image on the right is a cyclone system used where we were trying to separate two different materials. The first stage cyclone is smaller than the second stage cyclone. It has less residence time. In that cyclone, we're separating a heavier material coming from the process and returning it back to the upstream process. While the gases that go down to the second stage cyclone, we're removing ash and char from that stream, which is much lighter and more difficult to collect than the product in the first stage. So the second stage cyclone in this case is larger with a higher residence time for more efficiency. In the cyclone anatomy page, we discuss dust receivers, vortex breakers. They are very important for proper cyclone operation. They allow material to disengage from the spinning vortex as it comes down the cone of the cyclone. They also reduce abrasion in the cyclone cone and in the seal device below. Oftentimes there will be a rotary airlock or a double flap valve below the cyclone discharge. If the particulate is spinning directly on top of that, it can cause increased maintenance and wear on that device. For best result for the dust receiver, we recommend proper dimensions, and we've given some guidelines used here. These can vary by application, but this gives an idea of the relative size of a proper dust receiver. They can be pyramid or conical. Pyramid is less expensive and simpler to add access doors, but if you have sticky materials or ASME pressure vessel design, polished interior, the conical arrangement is probably a better choice. There are different types of inlets to industrial cyclones. The ones that CECO builds and that are fairly common in the industry are the two cyclones on the left. The Fisher-Klosterman cyclones are the second from the left, which is called the wraparound inlet style, or also called an involute inlet. In that design, the inlet sits outside the body and gives more distance between the inlet particulate and the outlet pipe to create some additional residence time, as well as minimize any short circuiting through the outlet pipe. The cyclone on the left utilizes a tangential inlet, and that's very common to see on standard efficiency cyclones and some high efficiency designs where the inlet comes in on the OD of the body. There's also a design not shown here that's a partial involute where the inlet sits midway between the OD of the body. Some helical design cyclones are used as well, and axial vane or axial cyclones are very common in multi-clone arrangements where there are multiple cyclones inside one chamber for a high collection efficiency. These are often a cast cyclone in those applications. Some of the process variables that exist for sizing a cyclone will be covered next. I mentioned before that cyclones are sized based on the gas volume. In that, we also look at inlet velocity. So inlet velocity into the inlet of the cyclone, there is some wide variability, but at the minimum, it's desirable to stay above 40 to 45 feet per second. Below this value, it is highly likely that a lot of the material can drop out in the inlet of the cyclone, which will cause irregular flow patterns going into the body and significantly reduce the collection efficiency. Now, as you increase the inlet velocity, we need to be concerned about pressure drop and erosion and particle attrition. As the inlet velocity increases, the pressure drop across the cyclone goes up by the square of the velocity change, so there can be a significant energy impact. In addition, erosion can vary by at least the square, sometimes the cube of the flow change or the velocity change. So that can also be a significant problem if you're dealing with an abrasive material. Particle attrition should also not be ignored. As the velocity increases, and if the particle is friable, it can actually break apart during that abrasiveness on rubbing against the cyclone sidewall, and the result would be the cyclone sees a finer distribution than what was accounted for in the design, and this would result in a lower collection efficiency than predicted. But generally, inlet velocities, they stay below 75 to 80 feet per second, but there have been applications where inlet velocities go up to over 200 feet per second. For pressure drop across a cyclone, that's another design consideration. If we consider that independently of the inlet velocity, obviously on the previous slide, increasing the inlet velocity increases the pressure drop. But there are other means to increase the pressure drop in a cyclone. We can change the outlet pipe or vortex finder dimensions. We can also alter the body and cone dimensions to change the pressure drop. So if you're changing pressure drop and the inlet velocity is okay in terms of erosion or particle attrition, then it's purely an economic consideration in terms of spending more energy to get a higher collection efficiency. Normal cyclones are typically between 3 to 8 inches of water column, and that varies depending on the gas density for the application. Now, if you're dealing with an ASME pressure vessel cyclone or a high pressure system, then the pressure drops can be several psig in those situations where the gas has a very high density. There are no real limits to the particle collection efficiency of a cyclone. However, there are practical limits in terms of size and economics. So cyclones can collect very fine particles. In fact, there are some collecting particles with average sizes in the 1 to 2 micron range for the system. These are usually very small gas flows, so the cyclone is extremely efficient or very large. Relatively to, it may not be a large cyclone, but the cyclone is large compared to the inlet gas flow being that's designed for. Most common industrial applications, we see cyclones that's very good on 20 to 30 micron, but there are some ultra high efficiency cyclones that get good efficiencies, 99+% in the 5 to 10 micron range, and sometimes below if we have a heavy particulate that we're collecting. This chart is an example showing for a single application, and this particular application was in the wood products industry on a planer mill application. As we move to the right across the horizontal axis, the cyclone model gets more efficient. And on the vertical axis is the outlet grain loading. In this application, we looked at multiple cyclone possibilities. And we see that on the right is a very high efficiency, ultra high efficiency cyclone with 4 cyclones in parallel. This cyclone is easily achieving a 0.01 grain loading or less efficiency. But as you move to the left, the cyclones get less efficient and smaller. The residence time is reduced. In that case, they become more susceptible to the higher percentage of fines in the dust sample. The blue, red, and green bars represent 1.5%, 5%, and 10% fines in the same sample. The reason this is important is the cyclone design and performance prediction is only as good as the data that we're provided. So if when you start up and actually put the cyclone in service, there are chances that there may be more fines than expected, or something may be going on in the process, generating more fines than when the sample was taken. So as a general rule, as cyclones have more residence time, they can better accommodate a higher percentage of fines in the system. So it's like building in some conservatism to your design. This chart shows the relative collection efficiency versus length to diameter ratio, or L over D ratio. The L over D ratio of a cyclone is the height of the cyclone, which is the cone plus the body height, divided by the diameter of the body. There are cyclones that are shorter with larger diameters, resulting in a 1 to 2 length to diameter ratio, whereas most industrial high efficiency cyclones are going to be have an L over D ratio of 3 or greater. It's often that with cyclones and dry particulate collection, we're going to be working with particulate that is combustible. And we must design cyclones for that to vent that deflagration correctly. It's important to note that venting a cyclone is different from venting a baghouse. For a baghouse, often additional vent area can be added to keep the P-red or the design pressure lower. For a cyclone, the only place the gas can exit is through the outlet pipe or through the cone discharge. And this is because if you put vents on the curved surfaces, such as the cone, the body, or even the roof, it can severely impact the performance of the cyclone. So since we can only put vents in certain places, the diameter of your vortex finder or the cone discharge, if venting in the dust receiver as well, will impact the design pressure of the cyclone. So if you're looking at systems, be aware that while a baghouse in the same system may be a 3 to 4 psi-G design, it's not uncommon for a cyclone to be much higher than that. It could be 10, 12, 13 psi even. In some applications where we have a high efficiency cyclone with the high KST or Pmax for the dust, it requires venting in the dust receiver as well to prevent going into an ASME pressure vessel design. And I should also mention, instead of venting, especially in an indoor application, you may consider chemical suppression. Chemical suppressing a cyclone will most of the time require mounting chemical suppression bottles on the curved surfaces of the units. Be very careful that the interior is maintained as continuous as possible. This may require machined repads, but it will also be noted that there will be some slight variation in the interior, a flat spot created, and that can affect performance. You'll need adequate access as well to maintain and inspect the chemical suppression connections after you start running. This is an example of an NFPA design cyclone for a steel DRI dust application, and we have explosion vents in the outlet manifold and using chemical suppression for the inlet and outlet isolation. This slide uses this is an NFPA design for a very combustible metal dust. We have explosion vents located in the dust receiver to stay under an ASME pressure vessel design. And this slide shows a high efficiency planer mill cyclone with explosion vents identified in red for where we're venting the dust receivers and the outlet manifold. I mentioned there are some common performance problems associated with cyclones. They can be improperly designed. We can have incorrect or inaccurate design data. There could be leakage into the cyclone, also material buildup or dents on the cyclone, and wear and abrasion are issues. And we'll cover each of these briefly in the next few slides. Some of the common design problems you'll see are short outlet pipes that allow recirculation or of the dust short circuiting to the outlet pipe direct from the inlet. Dished heads that are used without a false roof inside the cyclone. Poor or non-existent airlocks can allow leakage into the unit, and that can be part of the original design. Instruments or access ports installed onto the curved surfaces should account for a flush interior if at all possible. And if you have inlet elbows on the cyclone, it's important for those to be, if they're in the horizontal, to be situated so they turn in the same direction as the cyclone spin. This chart shows for a specific example the effect of outlet pipe length. As we can see, for outlet pipe number 4, we have a higher collection efficiency, even though for outlet pipe number 3 and 5 at different heights, and these are percentages below the roof or percent of inlet height. We get a much higher collection efficiency for outlet pipe 4. So if it's too long, we mentioned if it's too short, we can get short circuiting, but if it's too long, we can also get re-entrainment of good material that we would have collected. For the roof design, often you'll see dished heads for ASME pressure vessel applications. It's important to have a flat roof at the inlet of the cyclone. So this shows the difference in collection efficiency of almost 0.75%, which would be a lot of product, or if this was for an emissions test application, you would probably most certainly fail the emissions test without the flat roof inside. So some of the other common design flaws in cyclones are a lack of a dust receiver to separate the material before going into the discharge device, or no airlock at all. The outlet pipe can be too short, we call short circuiting, or a shallow cone angle. A very shallow cone angle is sometimes used to reduce height. That can have abrasion and performance issues, causing the material to prematurely wear the cone or also be pushed out into the clean gas system, clean gas exit. It's important to have good design data. If you're troubleshooting and the cyclone's not doing meeting its performance, the first thing is to check cyclone pressure drop and also confirm the gas flow rate. These two things, along with leakage into the cyclone, are probably covered 90 to 95% of the reason cyclones do not meet their performance requirement. And mentioning leakage, a rotary airlock can definitely be the subject of that leakage. As rotors wear and we lose wiper strips, you get air leakage back into the cyclone. Oftentimes, airlocks rotate at too high of RPM. They really need for a cyclone to be below 15 RPM, and if it's a very large airlock, they should be considered to rotate even slower. Large airlocks can create a fan effect that brings entrained air back into the cyclone and causes excess re-entrainment. We mentioned buildup and dents in the cyclone. If you get condensation on the interior of the cyclone, material can build up and stick to the wall, and in trying to keep the plant running, maintenance will often come and knock on the side of the cyclone to remove that material. This can create dents over time or hammer marks in the side of the vessel. The dents and the buildup, they cause an irregular surface inside the cyclone. It causes material to kick back to the center of the cyclone where it is re-entrained and exits the cyclone. So it reduces the cyclone efficiency. So some solutions for material buildup inside the cyclone is to install vibrators on the side of the cyclone hopper, to polish the interior. You can use special coatings. Also review the cyclone outlet sizing and discharge device sizing. These should be adequately sized for the material being handled. And if you could also add insulation or tracing to prevent the condensation from occurring on the hopper wall. Cyclone erosion is another issue to look for in maintenance and troubleshooting. If you have a material that's not abrasive in the ductwork, it's possible that it could be abrasive in the cyclone because we're pushing this material to the wall to be collected. This is another example of cyclone erosion. The bottom of the cone is a very key place to start seeing abrasion and erosion. And this example shows corrosion and erosion at the same time. And with this, I'll hand this back to Mary. Finish up the presentation.
Thank you, Mike and Mark. We really appreciate that. And before we we're running long here, so we're going to do one question here. And before we do that, I just want to go over the platform again. So if anyone needs to take their test and all, and anyone, if we do not get to your questions, don't worry. Like I said, we will definitely reach out to you, even if it's after the presentation. Once we're done here with the one question, we're going to go quiet on audio, but the platform will actually remain online and functioning. That way you can go in there, print out any resources that you haven't had a chance to, or finish up the test and print out your certificate. So again, for everyone who needs the PDH portion, the last two widgets are the ones that you need to be looking at. Once you have fulfilled all of your criteria, if you open up that certification widget, you're going to see a little tab there that you're going to be able to print out your certificate. And let me pull one question quickly. And when would you choose a cyclone for filtration over a baghouse?
Hi, Mary. I'll answer that. If the cyclone can get the performance required, then it's going to be the most economical solution in terms of, especially in terms of maintenance and ongoing energy cost. So generally speaking, if you have particles that are in the single-digit micron or even sub-micron, you're probably going to err toward a baghouse. But it also depends on what percentage of the inlet loading those represent. If they represent a relatively small percentage of the inlet loading, then it's highly likely the cyclone can meet the performance requirements. But if they're a large percentage, or it's mostly fines or mostly very fine powder, and you have a strict environmental requirement, then the baghouse may be the better choice. I hope that answers the question.
Okay. All right, everybody else who has not had their question answered, don't worry about it. We will definitely get back to you here. And just really do want to thank you all for attending our first event. We have several more scheduled for the rest of the year, and the full schedule will be released here soon. And we hope to see you at one of the future events. Feel free to email me if you have any questions, or if you want to make sure that you get on our list. And we always would be completely grateful if you would forward this on to your friends and any others who you feel might be useful, might find this information useful. So thank you again for attending, and I hope you have a wonderful day.